Welcome to this webinar called Measurement Microphones versus Pressure Sensors. I'm going to present this for you for the next hour, and there will be some practicalities. And this is on the next slide here. You're all muted, which means that you can't really raise any questions during the session. We are going to answer all questions that are written. So if you take a look to the right on your computer, there is a sort of a tab called questions. You can write your question there, and after the session, I'll read it and I'll try to answer all the questions. If you are interested in a handout of this presentation, it is also available. And you can actually click on the tab to the right called Handouts, and there you can download the session. So this is a little bit of the household things to keep in mind. Now I would like to go directly to the agenda, and this presentation is called Measurement Microphones versus Pressure Sensors. It sounds like it is some kind of a fight between two different sensors. It is not the case. And after this presentation, you are going to learn that this is measurement microphones are actually a pressure sensor. So it is just a very special sensor within the pressure sensor world. So the agenda for today, it is that we are starting with a presentation of GRAS, and this is only one slide, so that will not be very tiresome for you. Then we will talk about barometric pressure. We'll talk about types of pressure sensors. We will talk about static and dynamic pressure. Then we will go over to taking a review on measurement microphones, how they are actually fitting into this pressure sensor world. And then we compare microphones with pressure sensors. And then I have some practical experimental data to share with you for some real measurement with two different sensors, one pressure sensor and one measurement microphone. So all in all, this is what we are going to cover for the next hour. And I was having this presentation this morning, and it was taking roughly 50 minutes for the presentation, and then it was some time for questions if you have any. Great. I promised you one slide of explanation of GRAS, the company presentation, and we are three companies within a group called Axiometric Solutions, and it is three companies called AP, GRAS, and IMC. And what we are concentrating on today, it is GRAS. I'm working from the headquarters in Denmark, and this company GRAS has been around for almost 30 years, and it is founded by the Danish acoustic pioneer Gunnar Rasmussen. And therefore the name, it's actually coming from the acronyms from Gunnar Rasmussen. So it stands for Gunnar Rasmussen Acoustic Society. Today, we provide the widest range of measurement microphones, but also fixtures in the industry. So what you see in the middle here, it is a device where you can test headphones and headsets and so on. And you also see some standard microphones around this fixture. As I said, we are located in Denmark in Europe, and we have a little bit more than 130 employees, which is covering the R&D and manufacturing here in Denmark. Then we have a sales organization that are spread around the entire world with a number of own offices, sales offices, and then we also have a number of distributors for a lot of countries as well. A couple of words on myself. My name is Lars Winberg, and I'm the Business Development Manager. So I'm trying to focus on automotive, aerospace, and defense. And I've been with this company for the last 5 or 10 years, and within the acoustics, I've been for the last 35 years, I think. So that's about the company. So now we are going over to the real interesting stuff here. So the presentation is called Microphones versus Pressure Sensors. So let's first discuss a bit about what is the pressure and what is the different terms in this world. Well, first of all, if you take the Earth, you have a lot of air molecules, and these air molecules are by the gravity sucked down to the Earth. So it is more compressed close to the Earth than up in the end of the atmosphere. So it is a pressure against the Earth, the center of the Earth, and it is measured in Pascal, or equal to 1 Newton per square meter. If you talk with a metrologist, he will talk about hectopascal. And if you take the average pressure at sea level at the world or around the world, it is 13.25 hectopascal. And this is also called 1 atmosphere, and that is equal to the average pressure at sea level at the Earth's surface. So that means that if you're coming up to Mount Everest, 8,848 meters up, it will be less pressure because the air molecules are not that much pressed together, and therefore it is a lower pressure. If you're going even further up, it will be lower and lower pressure, and therefore you see the jet pilot here on the picture. He's having a pressure demand mask, which means that he can actually get oxygen in a easier way up here where it is low pressure and not so many air molecules. So this is how it works, and as I said, 1 atmosphere, that is the barometric pressure at the surface of the Earth. So when talking about pressure sensors, we need to put some basics into place here. And if you take the absolute zero pressure, which is in a vacuum situation, and then we have the atmospheric pressure, it's 1 atmosphere, or 13.25 hectopascal. And then we're putting in, if we're measuring the barometric pressure, we're measuring from the absolute zero pressure point up to the atmospheric pressure, or down to, really, because now I have reversed the scale in a way, because on the bottom it's the absolute zero. On the previous slide it was vice versa. Then we can measure the absolute pressure, and that could be below the atmospheric pressure or above the atmospheric pressure. And then we can measure also the gauge pressure, which is in between or around the atmospheric pressure. So these are the basic terms when talking about pressure sensors. And if we put that into the different types of sensors that you can buy on the market, you can see that we have these absolute pressure measurement technology or types. They are having vacuum on one side, and they are putting the pressure that we are measuring on the other side. So therefore we are comparing vacuum with the measured pressure, which means that this is an absolute measurement from vacuum situation and up to the measured pressure. Then we have a gauge measurement, which is the ambient pressure on one side and the measured pressure on the other side. So there we take in the ambient pressure, and that could be, for example, the barometric pressure at surface level, which means 1 atmosphere's pressure. And then we compare with the measured pressure on the other side. There are basically also 2 other types of pressure sensors, and they are described here. And one is called the sealed reference, which means that you can have another pressure than the vacuum on one side. And this is the reference pressure. And then you can do a measurement up against this reference pressure. So that could be 3 atmospheres, or it can be whatever if it is designed for this pressure sensor. We can also have what we call the differential pressure sensor, which means that you have a reference pressure on one side and you have the measured pressure on the other side. So basically four different types of measurements. So if you compare it with the atmospheric pressure, you have the absolute and the gauge measurement. And if you're comparing with a reference value, then you have a sealed reference or a differential. There are also other types of pressure sensors. So if we take a look at what different types it is on the market, you will find out that there are a number of different principles how to actually measure them. And one could be capacitive, it could be a piezoelectric, it could be optical, it can be a MEMS or resistive, and so on and so forth. So there are different sensing principles. It's also different media compatibility. So that means that some of the pressure sensors are for hydraulics and pneumatics. Some of them are for liquid and some of them are for air. There are also different types, and that was the previous slide you saw. It's actually the four types that we just went through: absolute, gauge, sealed reference, and differential. So if you put this all together, you can get a wide variety of different sensors for different purposes. When talking about microphones or measurement microphones, we can actually point out what sort of functionality or what sort of principle are used in measurement microphones. It is capacitive. It is a sort of a capacitor, and I will show you that later on. The media that we are doing the measurement in is air, and the type of it is a gauge one, because it is a gauge around the atmospheric or barometric pressure. So that's the measurement microphone. So what are we actually measuring when talking about a microphone, a measurement microphone? Well, if you take a look at this picture here, you will find out that you see the atmospheric pressure, the blue line, and you see a curve that is going on top of that. It is actually the sound wave that is superimposed on the actual atmospheric pressure as shown in this picture here. And this is very much the same as you see on this pool, swimming pool, where you see the waves. And these waves are very similar to a sound wave on top of the atmospheric pressure. So you have a small variation in the pressure around the atmospheric pressure. So if I'm now taking this signal and I'm actually enlarging it, saying it, what is the maximum sound level possible in air? Well, if you take a look here and do the analogy with a swimming pool, you can see here that in a swimming pool, the height of a wave on top of a swimming pool is actually defined by the depth of the pool. And this is actually absolutely the same, because we have the atmospheric pressure, and when we have a signal that are big enough to go up to the absolute zero pressure level, then you actually have the span in between here. It is 194 decibel. So therefore, if the atmospheric pressure goes up to a higher level, then you can actually have a louder sound wave than 194. And vice versa, if the atmospheric pressure goes down, you can have a lower sound wave. What if the sound, or what if the wave is actually bigger than 194 decibel? Well, that is possible, but then it is described as a shock wave rather than a sound wave. And then you have some other effects, some other things taken into account. So when talking about sound, the maximum sound level, it is 194 under normal pressure level. So now we have seen that we have a static pressure, that is the atmospheric pressure, and then in the absence of sound, and then if we put the sound on top of it, it is the dynamic pressure, that is the sound wave. And of course, if you would like to have a calculation of the total pressure, then of course you should put together the static pressure and the dynamic pressure. So now we have this fluctuation of the pressure around the barometric pressure, and you can actually have it in different frequencies, and this is defined as below 20 Hertz. It is infrasound, all down to 0 Hertz. And then you have the audible frequency between 20 Hertz and 20 kilohertz. And then you have the ultrasound, that is everything above the 20 kilohertz. So if you put that into another picture here, you can see from 0 Hertz up to 20 Hertz, you have the infrasound, then you have the audible frequencies, and then you have the ultrasound up here. And we have just learned that the highest level, it is 194 for sound, but this curve here is actually ending at 120 because the audible frequencies, audible levels are of course ending at roughly the level of pain, which is 120, 130 decibel, dependent on the individual human being. And then this dynamic range is also ending at 0. And it's not entirely true, because 0, it's usually defined as the level or the threshold of hearing for a human being. So you can actually have lower levels than 0 dB. You can have -2 dB, -4 dB, and that is hearable by some animals, for example. So this is just for the human being, that it is starting with 0. Great. So now we take the next step here and say, okay, now we have something that we call a pressure sensor, and we have something that is called a condenser microphone or measurement microphone. What is the differences and what is the similarities here? First of all, if you take a pressure sensor, most of the pressure sensors, they are static pressure sensors, which means that they are measuring something that is almost static. Nothing is really static in this world, but at least it is stable for some time. So if you take a sensor that is comparing the pressure with the atmospheric pressure, you can, for example, take the example of measuring the pressure in your car tires. There you put on a measurement device and you can see what is the pressure in your car tire, and you compare it with the ambient pressure, which means the atmospheric pressure. That is very much a static pressure because you don't have any fluctuations in the tire, and therefore it is a static measurement. Then in some cases for pressure sensors, you also have dynamic measurements. So you're only interested in what is on top of the atmospheric pressure or the barometric pressure. And therefore, sometimes they are called piezoelectric microphones, which is in reality a pressure sensor that works very much like a microphone, but it is a pressure sensor, and I will show you the differences later on. And if you take a condenser microphone, what is the range for that? Well, it is a little bit below 0 dB for some of them, and it goes up roughly to 190, 194 decibel, which is the loudest sound wave. So just for your information, if we are measuring something that is 0 dB, that means that you have a pressure variation on top of the atmospheric pressure with 0.0002 microbar, which is extremely small variations in the pressure. And if you take 190 decibel, that is a difference of plus minus 0.63 bar. So you can see it is really some very small, tiny fluctuation in the pressure that we can measure with a condenser microphone. And therefore, you can see here, if you take a piezoelectric microphone or a pressure sensor doing measurement, dynamic pressure measurements, then you will have a noise floor that are basically starting around 100 decibel, 100 decibel. And then you can't really see anything because the inherent noise in the sensor in itself is actually going to hide the real signal. Vice versa, if you take a condenser microphone and you're trying to measure 198 decibel or 200 decibel, this will be totally distorted, and therefore you can't really use that for that kind of measurement. But as you can see here, there is a certain overlap of the two sensors. So that means that you can use a traditional pressure sensor or you can use a condenser microphone. So just for curiosity, this is some measurements and some estimations. NASA were sending up a rocket called Saturn V, and that was measured to be 204 decibel. And 204 decibel, we have just learned that this is not really a sound wave, this is a shock wave. And the volcano Krakatoa that had an eruption many years, it was estimated to have a sound level of 310 decibel, which is again not a sound wave. It is more another type of effect. And this is a drawing of the Krakatoa. And this picture here, maybe you are asking if I'm starting to be interested in art here on my side. Well, it is actually Edvard Munch that painted this painting, and this is called The Scream. And The Scream has been inspired by this Krakatoa volcano eruption. So you can actually see the sky is filled with smoke and so on, and 310 decibel, it's probably not enough with just two hands over the years. Anyway, this is the overlap. If we are now taking a look at this gauge pressure sensor, or we actually start with a microphone. We see up here three pictures, and the first one is measuring the blood pressure. This is of course also some kind of a gauge measurement because we are comparing it with a pressure at the barometric pressure at the site we are at. We also have a microphone where we can sing into karaoke or something like that. And this is also using the same technology with a gauge pressure measurement. But then we also have pressure, measurement microphones that are using this way of doing the measurement. So how is an acoustic sensor or a microphone working? Well, you have in front of the microphone, you have a diaphragm, and then you have a backplate, and then you have the pressure that is actually changing the distance between the backplate and the diaphragm. And therefore it is called a capacitor or a capacitive microphone. So that if the distance between the two plates are changing, then you can get a signal that is equally big as the pressure on top here. So you basically use it as a capacitor, and then you let the sound wave push on this one, and you get the signal out on the other side. This is a little bit more schematic picture, and there you can see a house, you can see the backplate, you can see an isolator, so there are no electrical connection between, and you see the membrane on top here. And then you see a small air gap in between here. So this air gap is changing, and therefore you get a signal on the microphone. You also see a small air gap here, and this is of course the ambient pressure coming in, because if you don't have the ambient pressure coming in on one side of the membrane, you can't really do a gauged measurement. Then it is more a sealed reference measurement, because then you have a sealed area in here with some kind of a pressure. So therefore it is quite important to have this ventilation hole on a microphone. So this is another picture where you can see the different parts, and there you see the diaphragm, you see the backplate, you see the isolator, and you see the casing. So everything exactly the same as the schematics here. And this is a now assembled microphone where you can see that the ventilation is actually going through the thread here, and it is actually ventilated to the backside here. So this is the way a capacitive pressure sensor or a measurement microphone is working. If you take a pressure sensor, this is one example of a pressure sensor. This is an altimeter that is used for a skydiver, for example. It is very good if he knows what is the altitude of the location he's at, so he knows exactly where to use the parachute. So this is of course also comparing the atmospheric pressure with the pressure where he is right now, and therefore can tell the altitude down to the earth. There are different sensing mechanisms for pressure sensors, and it is a capacitive way of doing it. This is exactly the same as in a measurement microphone. You have a diaphragm and you have some air gaps to a plate, and there you can measure exactly the same way as a measurement microphone. You also have a strain gauge measurement where you have a diaphragm and you have some kind of a strain gauge that is measuring the strain of the diaphragm in itself. So that is just two ways of doing it. It is some other ways as well, but this is two of the most common ways of building a pressure sensor. Taking a look a little bit closer to a microphone. A microphone, as I said, is having a backplate, it's having a house and a membrane. And if you take a look at the membrane and the distance down to the backplate, it is roughly 20 micrometer. So it is not very big distance here. So the air chamber is very small in here. Then the elasticity or the variation of the membrane is even smaller. It is 5 nanometers. So that is the distance it is actually vibrating with. And if you take a look at what other measures of this is, and then you can see a hair on your head. It is roughly 100,000 nanometers, and this is just 5 nanometers. If you take the thickness of a hemoglobin in blood is 5 nanometer. So it is actually a very, very sensitive instrumentation, a microphone, and therefore you can measure down to very low levels, even down to 0 dB or below 0 dB. So when talking about microphones or measurement microphones, all the measurement microphones are controlled by international standards, and you have the most common or the most of the standards here. It is the IEC 61094, it is 61672, and some ANSI standards as well. So everything is very much dictated by the standards. So we know exactly the performance of a microphone, and also even the form factor, how big the microphone should be, and so on and so forth. So everything is described in the standards. So a microphone, as you can see here, it is a device that is converting the sound waves into an electric signal. And we know now exactly how that is done inside the microphone with a capacitor. There are many kinds of microphones. Most of our microphones is what we are calling measurement microphones. And measurement microphones, there are sensors that are complying 100% with international standards, IEC 61094-1. And you can see a number of examples out here where you can see different types of pencil-like microphones. There are also some other microphones, and if they do not meet all the specifications, only the performance criteria, but not the mechanical dimensions that is specified in this IEC standard, then we call them sort of a measurement microphone, but they have a different form factor. And this is a example of that. This is a GRAS, what is called a UTP, ultra thin precision microphone. And this is a very, very thin microphone. But of course, the standard is dictating this pencil-like type of microphones, and therefore it is performing exactly in accordance with the standard, but the form factor is different. And therefore, it is not what we call the measurement microphone. It is called a microphone or a special microphone, which is measuring equally as a measurement microphone. They're just different in size and format, in dimensions. So if you take a look at a product portfolio, you can see that we have microphones from 0.09 hertz up to 140 kilohertz. And if you take the dynamic pressure or dynamics of the microphone, it goes from -2 dB up to 193 decibel. And just for your information, that is equal to a variation in the pressure on top of the barometric pressure of 0.000158 microbar. And 193 is equal to plus minus 0.9 bar, roughly. So this is, you can see it is a very big dynamic range a microphone is actually having, going down to very, very low changes in pressure. Great. I said to you that all the microphones are having a ventilation hole, and this is just a warning. If you're using microphones, do not block the venting hole. And here you can see some of the installations from the real world. Here they have used some tape. I don't know why, but the ventilation hole is covered. And here you see in the engine bay of a car where they have taped the microphone to the surface. And then we are converting this gauged measurement around the atmospheric pressure to a sealed reference, meaning that we have a reference pressure inside, but we don't really know what sort of pressure we have on one side. And then we are comparing it with a pressure that we are interested in. So important not to cover the venting holes. Talking about microphones, they are described in this international standard, as I said, and this standard is sort of describing what is the reference environmental conditions. So there you will see that the reference temperature is 23 degrees centigrades. The static pressure, it is 101,325 kilopascal, which is equal to 1013.25 hectopascal, and relative humidity 50%. So if you remember the first slide I was putting on, that was the static pressure. That was the average static pressure at sea level around the world. So this is 1 atmosphere's pressure. So these terms are described in here, and everything is calculated out from this reference environmental condition. When you buy a microphone, you're always getting a calibration chart together with the microphone, and there you can see there is stated the reference conditions for this calibration. For the temperature, it was 23 degrees when we did the calibration. The relative humidity was 30%, and if you remember, in the standard, it was dictated 50% relative humidity, and the barometric pressure during our calibration before it was sent to the customer was 1005 hectopascal. So then, of course, this is not in accordance with the standard, and therefore in the data sheet for all the microphones, you will find that there is a temperature coefficient and a static pressure coefficient. So that means that you can see how many decibel per kilopascal it is changing, and then you can do the math, and then you can actually calculate what is the reference data for this microphone. So this is delivered together with all the microphones, measurement microphones and special microphones that we're having, and therefore you can combine it, or you can go back to the standards and you can trace them back to the reference conditions. When you have a pressure sensor and you have a microphone, you have a data sheet for both of them. It is not very simple to actually compare them because they are describing the different parameters differently. So if you take the sensitivity for a microphone, it is always defined as millivolt per Pascal. And if you take a pressure sensor, usually it is millivolt per PSI. And how are you now going to compare a pressure sensor with a microphone? Well, you have to have some kind of a conversion, or you have to go in and do the math in your office. So there are a number of different points here. If you take, for example, the inherent noise or the noise floor, that is always specified on a microphone in dBA, SPL, but only very seldom specified for a pressure sensor. So there are different ways of describing the functionality of the sensor. And GRAS, we have actually issued a book which is called Microphone versus Pressure Sensor, and it's a handbook, and it can be downloaded from our homepage. And this handbook is giving you the conversion between the two worlds. So therefore, if you have a data sheet you would like to compare with a microphone data sheet, you can do the math by using this handbook and do the conversion between the two. So encourage you to actually go to our homepage and download it. In the end of this presentation, or in the handouts that you can get, there is actually a web address where you can go in and you can search for the microphone versus pressure sensor handbook, and you will have it, and then you can download it from the site. So of course there are many different differences between the sensors, but I've been trying to do a very overall sort of comparison. And if we take some of them here, you can see that the pressure sensor, there are not really any international standard for how the form factor should be, how the performance should be, because there are so many different types of pressure sensors. It is for liquids, for hydraulics, and so on and so forth. So it is a little bit more complex to do a standard for that. For the microphones, on the other hand, it is very well defined in the IEC standard. So you can definitely see if they're following the IEC standard, then they're also performing equally or totally the same. And even the physical dimensions are the same if they are following the IEC standard. So therefore, you know exactly what you're getting when you're buying a microphone in accordance to the IEC standard. Specifications: pressures are specified in bar or PSI and in dB for microphones. Can you do a field calibration? Well, you can do that for pressure sensors, but it is quite difficult and you have to have special equipment. For a microphone, yes, it is very well defined how you're doing it, and it is also described in the standard. So you use a standard calibrator, you put it on, and then you can do a calibration before the test and after the test, just to ensure that the sensor in itself is working correctly. The sensing area, it can be everything on a pressure sensor. It could be a very big one to a very small one. And it doesn't matter, and we'll see that when we are coming to the end of the presentation. We actually have some applications where it is important to have a certain size of the sensing area. For the microphones, they are controlled by the IC standards, and therefore it is 1 inch, half inch, 1/4 of an inch, and then within brackets, 1/8 of an inch. And within brackets, because this is not described in the standard, but it is following the same standards as the 1/4, half, and 1 inch microphone. So when a user is going to use a pressure sensor or a microphone, he will have to set up some kind of a pros and cons, what to use in different applications. So this is actually not my table. This is taken from a user. It's a university in UK that has been using this as sort of a first very quick definition. And there you can see a microphone. This is capacitance. It is a variable gap between the backplate and the membrane. It is very sensitive, and it is unfortunately sensitive to temperature. So therefore, if you have a measurement point that is going to be placed in a 300, 400, 500 degrees Fahrenheit position, it is not a microphone you should use. It's something else, because the electronics and the metal in itself, it's actually not going to give you the right results in that temperature range. If you use a piezoelectric, there are some other issues to take care of. Sensitivity to vibration. So if you would like to do a test on a jet engine or a turbine or something that could potentially vibrate, the piezoelectric technology might not be the best, and so on and so forth. So you can actually see that there are a number of questions not really related to if they are measuring correctly, but some environmental conditions that can differ pretty much. So this is important to take care of. And now I'm going to go to the last part of the presentation. And this is actually an example. This is a practical example where we have been doing some measurements. And before I'm going into the measurement result, I'm going to take a bit of the theory behind. Because the application here, it is measurement of a fluctuating wall pressure in a wind tunnel. So therefore, what we are trying to find out now, it is how can we do a measurement measuring the pressure fluctuation on a surface. And that could be on an airfoil. It could also be on a fuselage. It could be on a car, could be on a windshield or something like that. And what we're interested in, it is to measure the pressure variations on the surface in itself. That can tell us something about where we have our laminar flow and where we have a transition region. And it can also tell you where you have the boundary layer, the turbulent layer, which is the layer that is actually creating some noise because it is interacting with the surface in itself, and it is potentially starting to vibrate the surface. And this is, of course, this is hydrodynamic forces, which means that this is created by the wind. So you can take, if you go on a Tesla, for example, you go in the city center very slow, you can almost hear nothing from that Tesla when you're sitting inside. If you go on the highway, suddenly you hear a lot of wind noise, and the wind noise is created by this boundary layer, the turbulent boundary layer, that is actually creating the noise for the driver. So if we take this as an example, we take a fuselage, and we can solve this with doing pressure taps, which means that we are having sort of a tube here, and the tube is connected with a longer tube and then goes to a pressure sensor or a pressure scanner that can actually scan all the points and see what is the pressure at any time for this foil. We could also use a surface-mounted pressure transducer that is actually clustered directly on the airfoil, or we can use an ultra-thin precision microphone that is placed in a fairing, and this fairing is actually designed for not creating any turbulence noise in itself. So it has a very nice angle up here, and the sensor in itself, it's only 1 millimeter thick. So we could solve this with a number of different technologies. Pressure taps are quite nice. On the other hand, it requires a lot of engineering, because you need to drill all the holes, you need to mount all the tubes, and you have to have space for all the tubes. So it's a lot of work. You could also use the surface pressure transducers, where you're actually gluing them directly on the surface, on the skin. And you can use the ultra-thin precision microphone, where you're gluing this fairing, and then you can slide the sensor in. So this is a picture from a customer that we have, and this is a Q-light sensor, where they have actually mounted Q-light sensors in an L formation over an airfoil. And there you can see it is called a high-intensity microphone. And this is a piezoelectric pressure sensor. And the acoustic pressure that it can measure, it is over the dynamic range of 100 to 194 decibel. So that means that the noise level of this one is pretty high. You can't really go lower than 100 decibel. Then we have the same configuration from another customer sold with this ultra-thin precision surface microphone, where it is glued directly on top of the on the airfoil again, in the same sort of configuration. And there you have a dynamic range of 54 to 184 decibel. So a little bit lower on the high side, but it is definitely a lower noise floor on this one. So now you have actually solved this task in two different ways. You have taken either the pressure sensor from Q-light, or you have taken a microphone, a very thin microphone, and you do exactly the same type of measurement. This is also an example. This is on a fuselage of a commercial flight, and there you can see, you can't really see the sensor in itself, but this is with pressure sensors or pressure transducers. And on the second picture, you see the same configuration, just using surface microphones. So basically, it's the same sort of installation, but you are solving the same problem, the same application with two different kinds of sensors. So we thought it was pretty important or interesting to actually compare the two sensors. So we have an in-house wind tunnel, and you see a picture of it down here. And we were setting up a test where we were using the MIC62 or MIC062 from Q-light, the LQ062 from Q-light, and then we compared the data with the GRASS UTP series. And this is ultra-thin precision microphone. So we were doing a side-by-side test. And before we are taking a look at the result, I'm just going through a bit of the theory here. Because I was mentioning previously that the sensor size is having an impact on the measurement. And here you can actually see what is the impact. If you have a pressure fluctuation that is bigger than the membrane size, then it will do a nice measurement, because the membrane is now going to go up, and therefore we have a good measurement. We have a distance in between the backplate and the membrane. And of course, if you are having a frequency going up, so it is actually double or half the size of the membrane, then you can see the membrane is actually going to go in two directions at the same time, and therefore it is not a very good measurement of the distance in between, and therefore you will have a null output because it is plus minus gives a 0. So that means that if you're going up in frequency for lower frequencies is fine, but when the membrane size is actually too big for the frequency, it is starting to go down, and then you can see the difference from a half-inch microphone and a quarter-inch microphone. So you actually see the effect of the sensing areal or dimension up here. So in a wind tunnel, it's a little bit of a difficult task to do the measurement in a wind tunnel because you have an acoustic component. And this acoustic component, that could be noise from the motor in the wind tunnel, that could be ambient noise from other sources, it could be wherever it comes from. And this is an acoustic component that is moving with 340 meters per second, which is the speed of sound. And then at the same time, on top of the atmospheric pressure, you have another component, and that is the hydrodynamic component. This is actually the fluctuation. This is the what we call the pseudo noise, or you can also describe it as the hydrodynamic noise, or the turbulent layer of the wind. So this is if you're on a bicycle, for example, and you can hear the wind in your ears. That is not really a sound, it is just the wind that is creating the noise. So here we can see the impact of the different parts here. So now we have a microphone mounted, and that means that we only have the acoustic component. So now we have no wind in the wind tunnel. So there you can see the half-inch microphone is the one going down faster, and then we have the quarter-inch, as we saw before. We have the ultra-thin precision microphone, and then we have the 1/8 of an inch microphone that is even going further up in frequency. So this is, of course, when you're increasing the frequency of the tone that we are playing now, then suddenly it is starting to integrate over the membrane, and then suddenly it is going down here. Now we take away the acoustic signal. Now we only have the hydroacoustic component, and therefore, if we are going, or if we are turning on the wind tunnel for 10 meters per second flow speed, then we can actually hear a bass tone, or we can hear up to 1 kilohertz. If you turn on the speed of the flow to 340 meters per second, that is equal to the sound wave, then you can see the difference here. So the lower speed, the lower in frequency, and the higher speed, the higher in frequency. So if you combine them, you have some effects on the membrane size dependent on if it is the acoustic signal or hydrodynamic signal. So in short, you can say if you have a big membrane, it is very good for collecting acoustic signal. If you have a very small sensing head, it is very good for collecting the hydrodynamic fluctuations. So now we are putting them side by side. So as you can see here, we have mounted them in a plate. So you have the UTP mounted with a soft fairing and then just some tape. So now it is 1 millimeter high over the surface. And then we have the Q-Lite MIC62 in a special adapter, which means that it is 100% flush mounted. Then we take a look at the signals, and if you take an FFT analysis on this, you can see here that this is the frequency. They're following each other very nicely, and then suddenly they are diverting from each other. So the light green curve here, that is the Q-Lite. it is going further up because the sensing area is smaller. And then the UTP is actually going down here. But what you see here also, it is that the noise level of the Q-light sensor is actually kicking in already at 70 decibel. So that means that everything beyond 60 decibel or 70 decibel, it's actually not hearable for the pressure sensor. While the UTP sensor, it's actually going down here. But if you have a tone over here, you can easily see that one because you have the noise level down at 40 decibel or something like that. So what we can see here, it is that they are within 0.5 decibel up to a certain level, and then the sensing element size is kicking in, and therefore it is rolling off. But then the inherent noise from the pressure sensor is actually going to kill the pressure sensor pretty quick after here. So in reality, you can easily have a signal or a tone of 10 decibel that is not detected by the Q-light sensor because of this inherent noise. So now we do a sort of a test with different wind speeds. So we have 20 meter per second, 26 meter per second, and 32 meter per second. And what is happening, it is that the breakout frequency is changing slightly from 1500 to 21 or 2400. For the low frequencies, they are following 100%, so they are totally equal there. And then if we take a look at the sound inflow, so now we have a situation where we have no flow and no sound, so nothing is happening. We see on the measurement microphone, nothing is happening, and the pressure sensor, we see the inherent noise. If we are putting sound on, we have a loudspeaker here. There you can easily see the tone, and there you can see it is 98 decibel. And you can see on the pressure sensor, we have no flow, we have only sound, 98 decibel, but you can see the background noise here. And if we have flow plus the sound, you can see that we have the same situation, 97.7, 97.8, but you have a much, much higher noise floor on the pressure sensor. We have a lot of other measurements using a side-by-side setup, but I'm not having time to actually go through them today. So if you're interested, we can arrange for a separate meeting. So just reach out after the meeting or during or send a mail to us, and we will set up a new meeting. So the conclusions for this meeting, the purpose was to help you to understand the differences between measurement microphones and pressure sensors. And conclusions, all measurement microphones are pressure sensors, specially designed for sound waves. The performance of measurement microphones are regulated by international standards. For certain application, both measurement microphones and pressure sensors can be used. And if you would like to compare data sheets, you can download this GRAS publication, the Microphone versus Pressure Sensor Handbook, and that can be downloaded from our homepage, www.grasacoustics.com.